Reactance is the electric resistance to energy flow in a capacitor or a coil. In this video I'm going to add a whole new chapter about resonant reactance, because it is assumed that reactance is constant at the resonant frequency, but it is not. Hi, my name is Ivo. I'm doing open source research into electric power generation. Reactance is not constant when a capacitor and a coil are resonant. This is because they do not only individually exchange energy with an external power supply, but they also exchange energy together. The coil and the capacitor together exchange energy. So the formulations for reactance calculation are correct, but they only treat the individual components in relationship to an external power supply, but not for the internal energy exchanges between the coil and the capacitor when they are resonant.
Definitions.
First, let me define some of the concepts that I will use in this video. First of all, the definition of reactance. Reactance is the resistance of a coil and or capacitor to the flow of energy. Now I'll define current as electric energy flow to make things more clear, since we have two types of energy flow. Two ways: as a magnetic conduction current, which is the magnetic field. It's like a whirlwind of energy flow around a conductor.
And this is the magnetic energy flow around a coil, swirling outside while it flows through the inside up.
The other current is the displacement current. This is a dielectric energy flow in between the plates of a capacitor when it is changing in voltage. Thus, capacitive reactance is the resistance of a capacitor to the displacement current, which is a dielectric energy flow, while inductive reactance is the resistance of a coil to the whirling magnetic energy flow around it. Polarity. A positive displacement current flows in a capacitor as a dielectric energy flow from positive to negative plate, and a positive magnetic current flows around the coil from the negative to the positive voltage connection of the coil. Both these energy flows can reverse in direction, which gives them negative polarities. Benjamin Franklin. In reality, the positive magnetic conduction current of a coil flows from negative to positive voltage end. This means in real life the resonant magnetic current sine wave should be flipped over 180 degrees in polarity. This 180 degrees phase shift looks like this. This is confusing, as most people talk about magnetic current flowing from positive to negative voltage. But this is only due to a convention based on Benjamin Franklin's assumption. He was proven wrong long ago, but still this false concept is used, and I wonder why. But it is important to keep these things within your mind. The holy trinities. We always have resistance, capacitance, and inductance. Capacitance is the ability to store electric energy in the dielectric field, while inductance is the ability to store electric energy in the magnetic field. And resistance does not store energy, but it transforms it into infrared electromagnetic heat waves, a radiation which usually is lost forever, while the capacitor and the coil can store and give back the energy that has been put into them. So all three of these are thus transformers of electric energy. Here's another trinity: voltage, magnetic conduction current, and dielectric displacement current, whereby voltage always needs two reference points, while the two currents only need one reference point, but have flow direction into or out of the coil or the capacitor. Always three. A capacitor will always behave as a capacitor and an inductor and a resistor. The way we shape a conductor makes one of those properties dominant, but these three are always present. A conductor can be wound as a coil or can be used to form the plates of a capacitor, but still it always keeps these three properties. So a capacitor also has inductance and resistance. And a coil has capacity and resistance. And a resistor also has inductance and capacitance. So to sum it up, we always have a voltage, a magnetic conduction current, a dielectric displacement current. And we always have capacitance, inductance and resistance. Bifilar coil. That is why the bifilar coil, which Nikola Tesla described in his patent 512340, is so interesting, as it uses the two series connected windings of a coil as a capacitor. So he made a coil that also behaves as a capacitor. He pictured this on the patent as a flat coil. But he also clearly wrote it can have many forms as long as the relationship of the windings creates an increased voltage difference which will charge the capacity. This is a quote from the patent. Page 2, line 7. I may wind any given coil, not only in the specific manner herein illustrated, but in a great variety of ways. Now, let's go back to reactance, the resistance to energy flow of the capacitor and coil. Is reactance constant at the resonant frequency? Now, it is very tempting to think that the reactance of the capacitor and the inductor are fixed at a given frequency. But that is not true when the frequency is the resonant frequency. Frequency is time periods per seconds. This is because the resonant frequency is a period of time in which the resonant sine wave completes a full cycle. And within this resonant cycle, the flows of energy are constantly transformed. And thus, the resistance to these energy flows also must change. The reactances are not constant for a capacitor or a coil when they are both resonant. The reactances change depending on the amount of charge present in the fields of the capacitor and coil. When a coil and a capacitor are resonant, there is a constant energy flow between the capacitor and the coil, back and forth. When one is charging up, the other is being discharged. To better understand this, we need to take a look at the individual components of the resonance system, at the individual resistance to flow of the coil and the capacitor. Independent reactances. Let me first remind you that there is always a little bit of pure resistance in the system, which will limit the maximum energy flow. To explain this topic, I will assume pure resistance is very low. If a coil is empty, in other words, it has no magnetic field energy and a voltage is applied to the coil endings, then there initially is no energy flow. Thus, the resistance to this energy flow must be infinite for an empty coil. It takes voltage and time to charge up the coil with a spatial magnetic field around the coil. If we take a look at the current, we can see it starts at 0 and then it rises to its maximum. While the energy flow is now rising and flowing into the magnetic field of the coil, the inductive reactance must have become lower for this flow to allow. And finally, when the magnetic field is charged to its maximum energy flow, the inductive reactance will have become 0, because the energy flow into the coil is now at its largest. So to sum it up, when the current in a coil is 0, the inductive reactance is infinite. And when the maximum current is flowing in the coil for the given voltage, the inductive reactance is 0.
Reactance of a charging capacitor.
For a capacitor it is different. The capacitive reactance behaves as the inverse of the inductive reactance. Let's look at an empty capacitor, so without a dielectric field no voltage is present. When a capacitor is empty, at that moment in time, we will see an infinite dielectric energy flow appear. This means that the resistance to energy flow, which is the capacitive reactance, must be zero. So the capacitive reactance is zero when a capacitor is empty. Then, while the capacitor is charging to a higher voltage level, the rate of energy flow will decrease, and thus the capacitive reactance must be increasing, and it will become higher and higher until the capacitor is fully charged. When the capacitor is full, then there is no energy flow. This means that the capacitive reactance of a charged capacitor is infinite. Reactance polarity, inflow or outflow. The capacitive and inductive reactances are always equal in a resonance system, but opposite in polarity. This is due to the perspective of the energy flow. The flow can be charging or discharging the coil or capacitor, which means there is an inflow or an outflow of energy. When a capacitor is discharging, it produces an energy flow out of the plate, which is a negative reactance. But while at the same time the coil is charging, thus it has a positive reactance. It has an inflow of energy, and it's now transforming the energy inflow to produce the magnetic field. So energy is flowing into one while simultaneously flowing out of the other. Therefore, the inductive and capacitive reactances, when resonant, are always opposite in polarity. Energy is neutral. It is the foundation of our universe. It has no polarity. It is neutral. Only the fields that are produced by neutral energy are polarized, have a positive and negative. And the flow of the energy has polarity, flowing into or out of the coil or capacitor, but the energy itself has no polarity. Negative reactance is assistance. The polarities of the reactances relate to the two energy flows, which are flowing into or out of the capacitor or coil we are looking at. When the energy flows out, then it is a negative reactance. This means there is no real resistance to flow, but actually an assistance to energy outflow. For example, when the capacitor is being charged, it consumes the energy flow into the dielectric field. This transformation can be reversed, whereby the energy flows out, and thus now the reactance is negative. So it's flowing out. So a discharging coil or capacitor always have a negative reactance, while charging a coil or a capacitor always has a positive reactance because the energy is flowing in. Resonant reactance and energy flow. Reactance can be seen as frequency-dependent resistance, but that is not really correct. When the frequency goes up, the capacitor's resistance to energy flow goes down, while the resistance to energy flow of a coil goes up. It appears as if the reactances at a given frequency are constant, but at the resonant frequency they are not. Simultaneous flow. In a resonant system we actually have two simultaneous energy flows. One is the dielectric energy flow between the capacitor plates, while the other is the magnetic energy flow around the coil. So the dielectric displacement current and the magnetic conduction currents are flowing simultaneously within a resonant system. These two energy flows can even flow in the same time and space when the coil is used as a capacitor plate. To visualize this, I will use the flow of non-compressible water as the magnetic current and the flow of compressible air as the dielectric current. Here we have two water bottles, one filled with air, the other filled with water. I will now connect these two bottles and allow the energy to flow, which is represented by the air and water. The swirling water is like a transverse magnetic current, and the air is like a longitudinal current. These two currents of air and water flow at the same time through the connector. Air moves up while water is moving down, and it's all in perfect harmony. Equal reactance but opposite polarity. Within the resonance cycle, the reactances of the coil and the capacitor are always equal in size, but opposite in polarity, due to the energy flows that are constantly flowing back and forth into and out of these two components.
Resonant reactance.
Let's now compare the individual graphs of the reactances of the resonant coil and capacitor. Let's first look at the resonant sine wave in the middle, so this here. FR stands for resonant frequency. In red, the voltage. In green, the real magnetic current. So that is negative 90 degrees phase shifted. And the displacement current, which is in blue. And this is positive 90 degrees phase shifted relative to the voltage. So not the conventional current is displayed, but the real magnetic current. Now, if you look at the voltage of the capacitor, you can see it is rising here. So this means the reactance must be positive as there is an inflow of energy. Here on top is XC, which stands for the capacitive reactance. We start at 0 when the voltage is 0 in the capacitor. When the capacitor is rising, it is positive. And when the voltage reaches its maximum, at that point in time, it reaches maximum reactance. Actually, it reaches infinite reactance. This is due to the blue curve, which stands for the displacement current in the capacitor. When the current is maximum, the reactance is 0. And when the current is 0, then the reactance is infinite.
The magnitude of the currents looks like a sine wave due to the resistance of the system. But if that resistance was not there, if we had only reactance, then those currents would become infinite in magnitude. But we have resistance, so we have a sine wave.
Let's continue. The voltage has reached its maximum and now it starts giving back energy into the coil, which starts producing a magnetic current. Now the reactance is negative as the energy flow has switched. Instead of an inflow, we now have an outflow of energy out of the capacitor. So the reactance is negative. We start with a 0 displacement current, so again an infinite reactance. Then the reactance declines to 0 when the displacement current is maximum, only limited by the resistance. And this continues all through the wave. You can see that each cycle of the reactance is a 180 degrees cycle from negative to positive and negative to positive again. Now let's look at the magnetic current in green. The magnetic current in green starts at its maximum, again limited by the resistance, else it would be infinite, but we always have resistance. The inductive reactance, which is the symbol XL, starts at 0 and will become negative. The current is declining. The magnetic current starts at maximum and starts declining. This means that the coil is now charging the capacitor. So the coil has an outflow of energy, which is represented by the negative reactance of the system. Again, the magnetic current reaches 0. There is no energy flow and the reactance is now infinitely. Note that I don't say infinite positive or infinite negative because infinite has no polarity. Then the coil starts charging again. It is increasing the energy flow into the coil. So we have a reactance which starts again being infinite. Then it is positive as the flow of energy flows into the coil and builds up the magnetic field. Then the energy flows out of the coil again. So we have a 0 point where the current is maximum again, 0 reactance, and then an outflow starts. So we have a negative reactance again. This current then becomes 0, whereby the reactance becomes infinite again. And again, this cycle repeats itself each half wave, each 180 degrees of the resonant cycle. And if we look at this picture, we can see that the reactances are equal in size, but opposite in polarity. Inflow stands for positive reactance and outflow stands for negative reactance. These moments in time where the reactances are 0 are very interesting. That is the perfect point for placing an impulse, when the voltage is 0. So, while charging and discharging, the reactances change. The reactances are not only dependent on the frequency and the size of the capacitance or inductance, but also are dependent on the resonant phase angle. Both reactances become infinite or 0 at the same time. The polarity changes not only at the 0 reactance point, but also at the infinite points. This means when it is infinite positive, it suddenly becomes infinite negative without becoming 0. And this is because the inflow of energy into the capacitor at that moment in time stops and becomes an outflow of energy. So you could say infinity has no polarity, just as 0 has no polarity. Conclusion. Resonant reactance of a coil and a capacitor are now known. They are always equal in magnitude, but opposite in polarity. There are two types of electric current: the displacement current in the capacitor and the magnetic conduction current around the coil. And the reactance of a capacitor is related to the displacement current, while the reactance of a coil is related to the magnetic energy flow, the magnetic current. And when both currents become 0, then the reactances are infinite. But when the currents reach their maximums in the resonant cycle, the reactance is 0 for both. The information in this video is shared open source. No patents can or will be applied. If you want to support my research, you can do so by donating on my PayPal account, which is listed in the video description. Thank you for watching and see you next time.